This is a review of geometric sequences. In question 1, we're asked to find the common difference, which is the amount that's added or subtracted in an arithmetic sequences. So if we have the sequence 5, 8, 11, 14, we can tell just by looking at it that we're increasing by 3. However, given any sequence, you can find the common difference by taking one term and subtracting the term that came before. So we'll also see that 14 minus 11 gives us a common difference of positive 3. Note that you can do this with any two terms. So I could take 11 and subtract 8 from it, or I could take 8 and subtract 5. In question 2, we're asked to find the common ratio, which is denoted by R, of the geometric sequence. So we have the sequence -2, 4, -8, and 16. Again, we can note just by looking at it, we're multiplying by -2. However, in any sequence, we can take the term and the term that came before and divide them. So in this case, 16 divided by -8 gives us a common ratio of -2. In question 3, we're asked to find the common difference in the sequence x, x plus y, and x plus 2y. So here's where it's important to note that process we said before. We can take one term and subtract the term that came before. So x plus 2y minus x plus y, that would be one way of finding the common difference. Another way would be take the second term and subtract the first term. So we could also do x plus y minus x. Both of those would help find the common difference. For number 4, we're asked to find the common ratio of a geometric sequence whose first term is 27 and fourth term is 64. So right away, if we kind of just draw out what we know about the situation, we have 27 as the first term, and the fourth term ends up being 64. So one thing we note right away is this is definitely increasing. If we have our second and third term, we don't know what exactly they are yet. But whatever we're multiplying by has to make the numbers bigger. So right off the bat, we can cross off answer choices 1 and answer choice 2. From there, if we examine the two remaining answers, we can think about this either as a geometric sequence where we have the first term is 27. We don't know what the common ratio is, but the exponent will be n minus 1. We could try, inside of y equals, putting in, perhaps, 27 times 4/3 to the n minus 1, and looking at the table. We could do that. In y1 and y2, we could do 27 times 37 over 3 to the n minus 1. Because again, for any geometric sequence, we take the first term, we multiply it by the common ratio, and the exponent is n minus 1. Comparing those two, we'll find out there's only one of them that ends up with a first term of 27 and a fourth term of 64. So go ahead and explore that on your own. All right, sorry about that quick issue. Here we go to number 5. In number 5, we see a figure with 8 shaded boxes in the first one, 12 shaded boxes in the second term, and 16 shaded boxes in the third term. So we can tell this is an arithmetic sequence because the common difference is adding 4. Remember that for an arithmetic sequence, we always write the first term, which is a1, plus that common difference times n minus 1. So for this arithmetic sequence, any term would be the first term 8 plus 4 times n minus 1. If we're trying to find how many blocks are in figure 35, we would replace n with 35. So for the 35th term, we would have 8 plus 35 times n minus 1. You might notice right away answer choice 1 is way too low and answer choice 2 is way too high. So if you evaluate that on your calculator, you'll find the correct answer. For number 6, we have something written in recursive notation. So just to kind of refresh us on what recursive notation looks like, I'm going to write the recursive formula for number 5, since we just talked about that. In recursive notation, you have 2 parts to your formula. The first part is what the first term equals. In this case, the first term was 8. So recursive notation would be a1 equals 8. The second part of recursive notation is the nth term. In recursive notation, you have the term that came before, and then how it's changing. So for this one, it would be an minus 1 plus 4. In number 6, we're asked to find the first 14 terms of a sequence with a sub 1 equals 40, and a sub n equals 3/4 a times n minus 1. So, we know in this situation the first term is 40. Based on the way this is written right here, we'll notice the term that came before is in this case being multiplied by 3/4. So the common ratio is 3/4, and to find each term, we're going to multiply by 3/4. So the first 4 terms would be 40, 30, 22.5, and 16.875. Number 7 asks us to find the 15th term of the sequence given here. We'll note that this one is multiplying by -2. So here we have a geometric sequence. For a geometric sequence, to write the nth term, we have the first term, which is 5, multiplied by the common ratio to n minus 1. In this case, the common ratio is -2. So the geometric sequence would be 5 times -2 to the n minus 1. The 15th term would be 5 times -2 to the 15 minus 1. So a15 would be 5 times -2 to the 14th power. When you do that, you'll see only one answer ends up being correct. For number 8, the 15th term of the geometric sequence, -5, negative square root of 5, square root of 10, -2 square root of 5. Well, we know that we can't be adding, because if you add square roots, they wouldn't end up with an increasing number. You can't add square roots unless they have the same root. So we know we must be doing some type of geometric sequence, and also it tells us it's a geometric sequence. So to find the common ratio, we can take one term and divide by the term that came before. So we could do the third divided by the second, or the second divided by the first. So we took the square root of 10 divided by negative square root of 5. We know that would be the negative square root of 2, because 10 divided by 5 is 2, and those are both under square roots. A positive divided by a negative makes a negative. So if we were going to write the nth term in this situation, a sub n would be equal to the first term, negative square root of 5, times the common ratio, negative square root of 2, to the n minus 1. So to find the 15th term, we can evaluate the square root of -2 to the 14th power and then multiply by the negative square root of 5. Negative square root of 2 to the 14th power is 128. So to write the answer in radical form, it would be negative square root of 128, or negative 128 square root of 5, excuse me. If you wanted to write it as a decimal answer, that ends up being negative 286.22. So hopefully that was a helpful review of geometric sequences.